Hey, welcome back. This is another episode of the archives, where I take old video footage and create something watchable out of it. First thing I wanted to show you is a plastic part that I have to make recurring customer part, and I just want to walk through the steps of machining it. So let's go. I start with the stock in the chuck and I face it off, and then I change to a CCMT 06 boring bar. For the face plunge, there is a recess in the face of the part, and in plastic and soft materials you can just take a normal boring bar and plunge into solid material without pre-drilling. It's not really a problem. You just set it slightly in front of center line, and then you can easily plunge into the material. As you can see, I'm taking a facing cut with the boring bar from the outside to the center to create a nice datum surface, and then I just plunge with the tool into the material. As you saw, the end of the insert was slightly in front of the center of rotation. That makes it work. Then I just bored it to size and faced it to the right depth. Using a 3-sided scraper to break the edge. Center drilling. I need a proper center drill because I have to support the part with a live center when I turn the OD. Drilling and tapping for an M4 thread. The center drill is of course bigger than the M4 thread, so there is still a center left. Okay, that's the first step. Doing the face plunge and the M4 thread in the center. And I do that to all of the parts now. Got the end machined on all 6 of the parts. Now we will clamp it a little bit shorter in the chuck, supported with a live center, and do all the OD turning. Turning the OD into the grooves. Okay, since I have the electronic lead screw retrofitted to my lathe, and I will do a separate video on the electronic lead screw, of course, because that will be interesting for quite a few people. I can use that for rough turning also. It can stop at a certain position for turning down shoulders. And right now I'm just checking my stops by rapid traversing to the extreme end of the travel. Yeah, there we go. That's the end of the shoulder I'm going to turn. And I have 0.2 of a millimeter allowance on the end for the shoulder to clean it up by hand without controlling by the electronic lead screw. And it stops automatically at the end of the given distance. It does not read the linear scale that I have on my lathe. It just counts the steps of the stepper motor on the lead screw. So it's not that accurate. It's within 0.05 of a millimeter. That's reasonable, very reasonable for most general machining tasks or for roughing work. If I need precision, I can disengage the lead screw anytime and do it by hand. And after we reach the end, I just hit a button and it rapids back to start. And you saw that it over traveled a little bit and then come back. That's to take out the backlash of the lead screw and the half nuts. Now I'm plunging the three 4mm wide grooves with a custom ground 4mm wide parting tool into the material. I touched off a tool on the end here. I'm just using the digital to get my dimensions right. Basically, I do not have to do any measuring while doing this. There we go. It's as easy as that. Checking the diameter of my plunge. Yeah. The reading calls out for 23mm without any tolerances, so 23.04 will do it. Yeah, that's that's all the OD work on this end. Next we will, after we did all of them this way, we will change over to the collet chuck, hold this on a 25mm collet and machine the end. And also cut off the waste stock. I have about 4mm of waste stock on there to hold it in a chuck. With such a soft material like the PVC, you need a little bit more material to hold it securely in the chuck, otherwise it could yeah, weeble wobble out of the chuck because it's so soft. Second side, change to a 5C collet chuck with a 25mm collet, and part goes in. I didn't bother to set up a collet stop just for 6 parts. And now we'll just whittle down this chunk of material to 35mm in diameter and 2mm in thickness. There we go. Another one done. Simple part. Very annoying material. When I say annoying, it's PVC is brilliant to machine it. You can take a depth of cut that's basically the length of your cutting edge on the insert, but PVC is a very low melting point, so if a chip rubs somewhere on the part, it will melt, and that's really annoying. So you have to be quite careful not to get a mess of chips spinning and rubbing against the part. And it's really hard to break the chip in PVC. I tried anything from 0.05 of a millimeter up to 0.3 millimeters of feet, and I couldn't break the chip with the inserts I have here in the shop. So yeah, that can be quite annoying. All 6 of the parts finished. Very easy part, but it's a recurring job, and yeah, nice part to make. So let's pack these up and ship them. People always seem to like shaper work, so here is a quick job that I did for a friend. 3 pulleys that needed to be bored and keyway broached or shaped. Keyway was 6mm wide, but I didn't have a 6mm wide broaching tool, so I made 2, one 4mm wide and one 6mm wide. And the idea behind that was that the shaper would not really handle a 6mm wide tool in a full cut very well. So I decided to do a 4mm wide keyway and then change over to the 6mm wide tool and open it up. In the past I used a narrow tool and stepped over to the side, but that's always a bit problematic. The narrow keyway shaper tools tend to get deflected when you try to do that. So using two independent tools works better. Here you see me right now cutting the 4mm wide keyway to get most of the material out. And in a second you will see me change over to the 6mm wide tool. There we go. The tools are just turned from, I think it's 02, and have a high-speed steel cutter in them. And they're ground on the tool and cutter grinder to the specific width. Here you can see from the top down into the bore, the 6mm tool creates its two lines, which indicates that it's on center. And then we just remove the remaining material going down. The shaper is really not the ideal machine for cutting keyways, but it's the only machine that I have for that purpose. A vertical slotter would be nicer. There we go, done. There's the tools and the holder. I use the keyway tools without a clapper box. There are the finished pulleys. A knife maker wanted to have some precision washers out of Eagle J, which is a very soft bearing material plastic from Aegis. And I turned them on the lathe and I tried to part them off, but it didn't work at all. The washers always cupped like crazy. So what I did, I went over to the milling machine and used a carbide slitting saw and a small rotary table to saw them off to a thickness of 0.2mm. And as you can see, that worked brilliantly. The slitting saw produces very little side pressure and cuts very freely, so making these washers was not a problem at all. And here you can see the finished washers in the left lower corner, along with some titanium screws that I had to make. This is an example of problem solving for weird parts. More parts for a knife maker. Here I'm making titanium screws with an T8 Torx head. I'm using the pantograph machine and mill the Torx head into the screws. It's a 0.5mm 3-flute carbide end mill, and I take 0.25mm deep cuts to create the profile. The overall depth of the profile is 1mm in the end. Here we can see the template on the template table with the follower to create the Torx profile. And this goes relatively fast. Per screw head it took me about a minute to cut the Torx head. The end mill is running at about, I think it's 9,000 RPM. This is the template for the Torx T8 profile, and I cut this on the CNC mill because that's easier than doing all the radii on the manual milling machine with the rotary table, of course. And when I cut it on the CNC, I also had it machine a 6mm bore in the center, and that's for a very specific reason there. That's so I can drop my stylus without the follower bushing into it. That gives me the center of this profile. That means the spindle is also in the center of this profile. Now I can use a dial test indicator in the spindle of the engraver to center on the part I'm going to machine. Just indicate it in. And when I'm done indicating, I can just pull out the stylus, put the bushing back on, and I'm good to go to cut the profile. I didn't cut the Torx head into the titanium screws on the easel CNC router because I tried it, it works, but it's not as good as I want it to be. The easel is just not built for steel and titanium, which is quite obvious when you look at it, but I had to try it anyway. So I decided to use the pantograph engraver here, which is made to do steel and basically it's a tool room machine. This machine was designed for engravings in the tool room, even in mold shops when you had to do engravings in molds that later will show up in the finished injection molded part. So yeah, this machine is up to the task, and by the 20:1 reduction that I set up here, I get an incredible precision, and also the forces needed to move the stylus around are very, very small, especially as I'm using a 0.5mm end mill. 0.5 street fluted carbide end mill. And here you can see one of the Torx profiles I cut as a test into a piece of scrap titanium through the microscope, and as you can see, it comes out very clean and very crisp. I did tests on the easel before and they did not look as nice. Also here you can see some of the titanium screws that I had to make for this job. All M3 threaded, all with T8 Torx head. I got this set of angle blocks from ArcEuroTrade in the UK. Cost about $50. You can get these way more expensive from, I think, Brown & Sharp and Mitutoyo should sell something like this too. And they are relatively useful. We have some shop made at work, and you can just drop them in a vise and set apart on an angle very quickly. You have 1 to 5 degrees in 1 degree increments, 10, 15, 20, 25, 30, 35, 40 and 45, and you get 1/2 and 1/4 of a degree too. These two are just parallel rises if your rise jaws are too high and the part is too small, so you can get the angle block higher up. And you can also add this half angle to one of the given angles. And as they're relatively inexpensive, I wanted to see if they are usable for me in the shop. I'm going over to a surface plate and I will set up a small, simple test to check them for accuracy. Overall, make quality looks good. The grind is really good. The surface grinding really looks good. They are deburred, but they're razor sharp, which is okay for me. They are deburred, but not chamfered. As I said, which is okay for me. But you might see that some of them are a bit crazy looking in the camera, but that's just the protection oil or wax or whatever they use to keep them from rusting. They were all individually wrapped in oil paper, which is quite tedious to open up all of them. It's like buying a gauge block set and each individual block is wrapped. Quite annoying. I'm checking the angled support pieces from ArcEuroTrade on the surface plate with a sine bar and the electronic indicator. If the angle matches what's engraved on the piece. There's a 5 degree angle block, sine bar set to 5 degrees, and I have my electronic indicator set to 10 micron range. That means from center to end of the dial it's 10 microns. I'm not going to move the indicator itself, I'm moving the setup on the table, so I do not strain the cable and change the reading. So we start over here and we zero it out. There we go. That's this side, and now we push it over and we watch the needle. Going right is plus, so it gets higher, and needle left is lower. Okay, we are 2.4 microns lower on this side than over here, which is 2.2 microns is not very much. So let's write it down. 2.2 micron over a distance of 50 millimeter. I will do the math. So I did the math, how much of an angle error this is, and it's 2.5 thousandths of a degree, which resembles 9 arc seconds, which is pretty little error. I will check a few more of these angle blocks, but I hope they are all within that range, so that's pretty stinking good for a set of angle blocks that costs $50. I'm slowly going through all of the parallels, the angle support blocks. This right now is a 15-degree one. It's already zeroed out, and I'm going to push it over to measure over the whole distance. And as you can see, we are around 2 to 3 micron error over 50 millimeter distance. It's not terribly good, but it's also absolutely not terribly bad. Just keep in mind the price. Always keep the price on these things in mind, and the intended use. These are not angle gauge blocks, not in the slightest way, but they're perfect for a quick and easy angled setup on a mill, or even for minor tasks on a surface grinder. So, seems like we cleaned out the archives for now. Hope you enjoyed. Thank you all for watching. Have a great 2018 and see you next time.